Let us start. So hello and welcome to episode 2 of TenzorGEO webinar series. This part focuses on principles, methods, and application of the passive low frequency method in the oil and gas industry. My name is Lev Frenkel. I'm an analyst at TenzorGEO, and I'll be hosting this webinar and looking after the technical side of things. If you have any questions you'd like to ask Dr. Bitrus, Director of Sales at Tenzor, who will be presenting, please send them to everyone's chat at any time during the presentation. You can do that by clicking on the chat icon at the bottom panel of your Zoom screen. And without further ado, Roy, over to you.
Thank you very much, Lev. Good afternoon to everyone. I'll just share my screen now so everyone can see my slides. So welcome everyone to the second part of this three-part series. I'll be talking about low-frequency seismic sounding technology. As always, who are we? TenzorGEO. TenzorGEO is a micro-seismic technology company, and we are pioneering the offshore development and deployment of low-frequency seismic as a direct hydrocarbon indicator in the North Sea. Over the next 30 minutes, I will be talking briefly. But before that, please hear our details in case you need to contact us at any point in time. So let's jump straight into it. So I'll be talking about the low frequency seismic, its theoretical background, just so that we have a very good understanding, its methods, application, and I'll be taking a case study each, onshore and offshore. So let's start with the basics. What is low frequency seismic? Now, low frequency seismic sounding is based on analyzing spectral properties of low frequency between 0 to 10 hertz of natural background seismic that changes above oil and gas deposits. Here on the right-hand side of the spectrum, we notice an anomalous amplitude contrast between the hydrocarbon-bearing rocks and the surrounding media, as opposed to the low amplitude contrast in the absence of a hydrocarbon-bearing rock on the left side of the spectrum. So the LFS method is based on the mechanics of fluid saturated, fractured, and porous media. And I'll briefly discuss the theoretical background of the low frequency seismic sounding method under these three topics: the physics of the phenomenon, the impulse response, and the resolution. So one of the main parameters used to study the nature of wave propagation is the acoustic impedance. Now, acoustic impedance is the product of density and seismic velocity. Therefore, it is the opposition of a medium to a longitudinal wave motion. It is an important parameter with respect to the transfer of acoustic energy between two media, as it characterizes the relationship between the acting sound pressure and the resulting particle velocity. Now, the relevance of acoustic impedance is because of the real part and the imaginary part. The real part is the active resistance of the acoustic impedance and is associated with friction, energy loss, or dissipation, while the imaginary part is the reactive component and is associated with the reactions of forces of inertia and or elastic forces. So it can be either inertial or elastic. Now, in addition to acoustic impedance, the concept of specific acoustic impedance is used, and it is expressed as the ratio of the effective sound pressure to the effective particle vibratory velocity. So for example, in the case of a plane wave, the specific acoustic impedance is equal to the wave resistance of the medium. Now, the difference in acoustic impedance between rock layers affects what's known as the reflection coefficient. Now, the reflection coefficient is used to define the reflected wave with respect to the incident wave. So for practical purposes, the reflection coefficient and also what you call the transmission coefficient are used to describe the ratio of the intensities of the reflected wave and the transmitted wave to the incident wave intensity. Now, let me explain. Here in simple terms, you have two rock layers, or in this case, media 1 and media 2, with different acoustic impedances. When an incident wave here in blue hits the boundary of media 1 and 2, that wave will be partially transmitted and partially reflected. So, if media 1 and media 2, however, have the same acoustic impedance, then there will be no reflection of the incident wave. All you would have will be transmission. To help us understand this further, I want you to watch this animation here as it moves with a high peak. It starts off with a high peak and boom, it hits a boundary. And when it hits the boundary of medium 2, the wave changes form and intensity as it transmits through the medium. Bang, you can see it here, well reduced. You also notice that when it hits the boundary, it reflects back to where it came from. This is a very basic principle of how waves are being transmitted. Now, next, and it's important to remember that because we will be pointing or saying things later on, and it will all refer back to this basic principle. Now, next we'll move into what's called the rheology of hydrocarbon saturated reservoirs, or in simple terms, the deformation and flow of hydrocarbon in saturated reservoirs. So the assumption that a hydrocarbon saturated reservoir is characterized by anomalous reflection of low frequency waves is based on a combined influence of several factors. And here we'll consider three: compressibility, viscosity, and displacement of oil. So compressibility. This means you can change the volume of a fluid, say in a container, by applying pressure. Now, oil and gas is compressible, and in a porous reservoir rock or a rock volume, this oil and gas will affect the contrast of impedance. Hence, oil contained in a porous reservoir will have a lower acoustic impedance. Remember, acoustic impedance, which we just talked about. The second is viscosity. This simply means resistance to flow, and oil is viscous. So as you can see in the diagram, there are different types of oil. These are engine oils with different shades of color, which also give you an indication of the different viscosities. Now, viscosity is relevant because it leads to what is known as absorption of the seismic waves, which in turn creates an additional acoustic impedance, which then leads to the formation of the imaginary part of the reflection, which we talked about earlier on. So finally, we have the fluid displacement. This is just fluid or hydrocarbon movement in the reservoir. It is important to know that crude oil has no inherent ability to expel itself from the pores of the reservoir rocks in which it is found, except it is forced out or displaced by the accumulation of other fluids, such as gas or water. Now, fluid flow in the pores of a rock media creates a slow wave, what we call a Crookes wave. This wave leads to the energy dissipation of wave that is transmitted through it. Hence, it leads to absorption, which adds up to the total absorption, thus affecting the reflection coefficient. Now, it is important to know that, let me just pause this here. Attenuation is an inherent property of the rock causing energy losses and leading to velocity dispersion. So across the slot layers, attenuation is part of the property. Now, oil and gas deposits are an anomalous zone in the low frequency range, which has increased absorption at low frequencies. And as you can see here, you have an oil layer and a hydrocarbon layer here. So the reason for absorption is a multi-phase structure of the deposits, consisting of a rock skeleton with varying degrees of velocity and a mobile phase, oil and gas. As a low frequency wave passes through the media, the mobile phase appears here and there in the fractured porous rock skeleton. Now, during this process, the internal friction between the oil and the fractured rock leads to a slow dispersive wave, which transforms into thermal energy, thereby causing absorption. You can see the change there as opposed to on the right-hand side as opposed to the left-hand side. And this is as a result of hydrocarbons. So the contrast of absorption, the contrast of absorption from the thin layer results in an anomalous reflection, as we can see. This effect is almost never observed in the case of water-wet formations, since the difference between the physical properties of water and the rock skeleton are insignificant. Now, I'll talk briefly about the impulse response and the resolution to just some of the theoretical background. Now, impulse response is basically the way seismic waves propagate in a geological environment or medium. Waves are generally classed into two. We have traveling waves and standing waves. Now, here within the traveling waves, we see two waves, one going back and the other one coming back forth. So we have green and blue. And as you can see, the green moves to the right while the blue coming back to the left. These are traveling waves. While the red one that goes up and down, becoming a crest and a trough, is a standing wave. Now, the standing waves can be attributed to the vibrations of vertical P waves, which is the target wave of low frequency seismic, and can be recorded by the Z component of a seismic sensor. Now, seismic resolution is a measure of how large an object needs to be in order to, I'll just leave that playing while I'm talking, in order to be seen, detected, and resolved in the seismic. And impulse response of a homogeneous media with one thin layer of lower impedance has a modal spectrum structure, which also has what we call spectral peaks. In other words, the impulse response will have multiple occurrences of waves or peaks. And the peaks that occur the most in the spectra indicate the values or the zones of interest. Now, the peaks are numbered in order starting from 0. And the low frequency seismic technology depth resolution depends on the modes in the spectrum used for interpretation. So we see this here. In the stratified geological medium, there's a frequency that's inherent in it. Now, while oil and gas deposit introduce additional contrast in the cross-section that causes changes in the structure of the spectral maxima. So you can see here a different spectra with this hydrocarbon layer. Now, if we change this, we see a change that's related to the fact that hydrocarbon deposit is present, and it causes this abnormal reflection. Now, the change in spectra increases again as we go further down the depths of a reservoir. For example, if the hydrocarbon layer changed with depth, you would have a difference in spectral properties. Now, this is in line with Professor Bitrus's hypothesis that abnormal spectra from hydrocarbon reservoirs are resonant in nature. So the LFS sounding method involves 4 main stages. We have onshore and offshore data acquisition. We have the processing of acquired LFS data. We have well data analysis and numerical model simulation and interpretation and results. So to acquire passive low frequency data offshore, we will first create an appropriate design based on the field size and target depth formation, which we would deploy our freefall ocean-borne seismometers to, which is well equipped, as you can see in this diagram, with broadband sensors, a digitizer, a GPS synchronized microprocess clock, large memory, batteries enough to last 18 months in sea, and weights to ensure good coupling. So very briefly, my next slide will show a video of the deployment of this ocean bottom seismometers to the seabed and how we acquire this LFS data. So we see the OBSs arrive in a containerized version. They are now fastened onto anchors. Fully assembled with batteries, pressure tube, and they are taken to the warehouse, sealed, tested, calibrated. Generally, we require 2 sea baskets or 3 and a working area on the vessel. So here you see preparations to deploy these OBSs. There are 2 versions there, the Namu and the Lobster. The same thing, just different versions of OBSs. One's the new generation, the other one is old design. It's also important to know that we don't need specialized vessel. All we need is a vessel that has access to a crane that can leave up to 2 tons, basically, and just enough space for the sea baskets. Here's our beautiful team. And so the OBSs are now prepared for deployment. They are GPS located, so they are deployed according to a specified grid. And they're released by freefall. We can monitor the descent using an ROV. It's good to know also that the weight of these things is massive. It's about 30 kilograms in water. That's the water wet weights. Boom, that's a good coupling, sign of a good coupling. Now there's a tolerance for the deployment of these OBSs on the seabed. So it doesn't matter if they fall within, as long as they fall within the tolerance, then they're fine, tolerance limits. So the ROV now can be used to reposition the OBSs depending on the size of the field and the number of OBSs deployed. We can redeploy them accordingly. So once recording is done, the crane sends down an anchor line and it is hooked onto the OBSs and is resurfaced. All stations will be recovered. The data will be downloaded, processed, and checked, just to ensure that we did get enough long hours of recording. Typically, you would be recording for nothing less than 12 hours in the seabed. There's no source, so that means everything was done in an environmentally friendly and safe way. We don't have air guns or anything, no source, no active source. We don't require much of a very specialized vessel. So that's one of the things that makes this solution quite attractive and cost effective as well. So after acquisition, we now move into data processing and filtration. So the goal of the LFS technology data processing is to obtain spectra of the vertically directed P waves from ambient background microseismic noise. However, this also comes with noise such as Schulte waves, which we'll see typically on the seabed, and Rayleigh waves if you were doing this onshore. It is important to understand the difference between offshore and onshore raw microseismic data. Now, offshore records have increased amplitudes from oceanic wave noise in the range of 0 to 2 hertz. So this typically here would be your noise range. Now, this covers the target frequency range of 0.6 to 1.9 hertz, which we anticipate contains a valuable part of vertically directed P waves. So while onshore ocean wave is significantly smaller by amplitude here and placed around the 0.5 hertz, usually onshore the problem is man-made noise placed at high frequencies between 2 to 4. So to effectively suppress low frequency noise, it is necessary to increase distance between the pairs of sensors that will be used to acquire them. So onshore records are filtered using the linear prediction algorithm, which works well and gives you the target BP signals. Onshore, we also use 2 simultaneous records from the Z components of 2 sensors within a defined station-to-station distance range. There's one problem though. Its method of filtering did not work in our offshore trial in the North Sea, as it doesn't efficiently suppress the waves which are coming perpendicular to the line which goes through the pair of the observation points as seen here. And so for the offshore recording, we updated our filtering procedure to an adaptive filtering method where we applied 3 simultaneous observation points, which allows for better suppression of the Schulte waves. Here we see an amplitude frequency spectrum before and after filtering using the most effective filtering workflow for offshore records, which is our new adapted filtering method. So while the processing for data acquisition is underway, we would acquire from the client details about the wells within the study field, such as a vertical seismic profile or depth, pay thickness, and wireline logs. This information will be used for numerical simulation and interpretation, where we will QC our filtering and simulation stages by matching filtered spectra near wells with simulated spectra. Next, we will perform numerical simulation, where we'll prepare 1D and 3D models using the VSP and other conventional seismic data, such as structural and isochron maps. The objective is to form a spectra of the responses in the model with the absence and the presence of a hydrocarbon saturated reservoir. And this is done in order to detect interpretable signs in the observed spectra in the field of study. Now, if you remember in part 1 of this series, I mentioned that one of the issues faced by companies who delved into low frequency seismic was that they didn't take into account the geology cross-section of the study area. This is very, very important. And we at TenzorGEO take this into account. And then we perform a numerical simulation of the microseismic waves. This is to determine the shapes of the spectra over the section with the hydrocarbon saturated reservoir and also without it. Our numerical model is based on the Kevin-Voigt model. Finally, we move into the interpretation stage. Now, in order to perform a quality control of the filtering and the simulation stages, we compare acquired spectra with modeled spectra and evaluate the similarities using a Pearson's linear correlation coefficient. As a result of this, maps are created. One of the acquired data and the other of, just give me a second, let me bring that up. So, so we would have two maps that are created, one of the acquired data and the other one of the modeled spectra, or the one that has been used in modeling. So one thing that we also need to acquire as well, or which will happen in the process of the acquisition and the processing, will be that the maps that we'll generate will have to match the models that we have created. So we create maps that are matched with the simulated spectra of the model with hydrocarbon and the one without hydrocarbon. Then finally, we do what's called a correlation coefficient, where we rank the final simulated and the observed spectra into one map, and we rank this into a potential hydrocarbon probability map, which will have high, medium, and low hydrocarbon potentials, as seen in this figure, where the areas with high, colors, darker colors, give you an indication of the highest probability of hydrocarbon, while those with the lower colors are less probability of hydrocarbon. Now, I'll summarize the workflow with this diagram. Here we start with the acquisition, design, and data plan. So we would first design a grid for the field, depending on the grid size. Then we would deploy these ocean bottom seismometers here. We will now process the data which we've acquired to filter noise, such as the Schulte waves. The result of this will be an actual spectral curve of vertically directed P waves by Z component. We will now use the VSP that we've acquired from the client here and the conventional seismic, or what you call an isochrone map, to construct a velocity model with oil and without oil. We'll now perform a numerical simulation on these models by applying a flat impulse on the top of the models. Now, the surface vibrations will be recorded in both cases. We will now process the Fourier spectra of these two models, and we will compare that with the real spectra in this, as seen in this diagram here. And the correlation maps are built and will take into account the hydrocarbon prospectivity of the area as well. So finally, what we would have here will be a match between the actual spectra, that's for the two simulated spectras that we have done, the one with oil and the one without oil. And the result of this is this blue-red correlation map here, which is then ranked into a hydrocarbon potential map with high, medium, and low hydrocarbon potential zones, as seen in this one here. So this sums up basically the work method, or the method workflow that we would use in TenzorGEO. So the application of this technology is within the geological exploration is quite useful, quite handy, and can be used to complement current existing exploration campaigns and data. So it can be used for forecasting of oil and gas prospects of an exploration area. We can use it to delineate hydrocarbon reservoirs. We can detect hydrocarbon accumulation in non-structural traps. identification of bypassed oil in watered out pools, and also identification of sweet spots for drilling. And in the UKCS, it's very important for small pools, for identification of small pools, and that's one of the main targets as well for us. So with time not on our side, I'll move straight into the onshore case study. So one of the applications of LFS technology, aside from identifying hydrocarbons, is to de-risk drilling itself. A good example is seen here in the survey done at the Caspian Depression, Russia. The task was to identify heterogeneous zones in a vertical section located above an identified condensate pool at 4,000 meters of depth in order to minimize complications during the drilling of production wells and also to avoid accidents. Now, due to the presence of salt dome tectonics, the LFS studies were carried out using 3D numerical modeling, which allowed the prediction of the presence of inhomogeneities above the main productive horizon. Now, heterogeneity was understood to be the presence of zones of decompaction. So that's layers with abnormally high reservoir pressure and natural or technogenic hydrocarbon deposits. So the obtained results were analyzed jointly with the clients, involving data on complications in the drilling processes in the wells that were already drilled before the survey. Now, the analysis that we conducted showed good agreement of the heterogeneities that was identified by the LFS method with the intervals of complications in drilled wells. So in summary, the onshore application of LFS has been successful in the past 14 years with an over 85% success rate, where the LFS forecast was confirmed with 131 wells out of 154 wells that were drilled in total. Now, offshore is a different beast. Here I present 4 maps, basically. Starting from the left-hand side, one is a map of correlation between the actual spectra and the simulated spectra in the absence of hydrocarbons. And the other one is a correlation between the actual spectra and the simulated spectra in the presence of hydrocarbons. The other one, first, in the absence, this is in the presence. And thirdly, is a map of normalized correlation coefficients, which characterizes the presence of oil. So the third map is used to transform to a probability hydrocarbon presence map. So according to this map, the hydrocarbon deposit, which is this one here, within the study area is located in the northeastern part of the survey with an estimated hydrocarbon boundary, defined by a probability of 50% along the observation points of 2123 and 222. Just somewhere around here. So a comparison of the new position forecast of the boundary of hydrocarbon deposits to the position of the boundary provided by the operator showed good convergence and indicated good potential of the viability of this technology in offshore conditions. So this kind of sums the end of this talk. This is typically what the client will be receiving from us as a job, and this will come in 3D models or 2Ds depending on what the client wants. So in general, one of the main tasks of geological exploration and development is to select a location for exploration and producing wells. And the presence of a structure just doesn't guarantee the presence of hydrocarbons, as conventional seismic surveys are usually aimed at studying the geometry of the trap and evaluation of formation properties, which do not expressly answer the question of where is the hydrocarbon. So relying only on the data obtained by traditional seismic exploration poses a risk of drilling a dry well. And this is the opportunity that LFS, our low frequency seismic technology, presents to complementing existing geophysical data by directly identified hydrocarbons, which will aid in the planning and the position of wells. So with that, we come to an end. I would like to invite you to the third talk, which will be happening on the 11th of June. And we'll be looking at full wave location technology, which is used for identifying fractures, fracture propagations, and also monitoring of fluid flow, which also can be used in the areas of potentially carbon capture storage, monitoring the evolution of CO2 within a reservoir, or the evolution of injected fluids to maximize recovery within a well or within a field. I will take any questions from here. Thank you for listening. Let me just, I think I need to log out of this to be able to see the questions that have been asked. First of all, yes, this presentation will be available on YouTube. And I have one question here from me, if that's okay. This question has been asked multiple times, and I think it's quite important that I just address it here. Says, is residual gas a risk in trying to detect hydrocarbon using LFS? No, not really, and I'll tell you why. So the anomalous effects in the low frequency field or the vertically directed P waves from a gas reservoir is actually strong, and for gas is actually even stronger than if you had for only oil, so because it can detect both gas and oil. So of course, residual gas in the form of accumulations at a certain depth interval will create its own anomalies. So we can set these depth intervals as gas saturated in the model, while we also look for oil and gas deposits. So we will tag them and identify them as heterogeneous gas. The LFS method will allow us to search for hydrocarbons in several target horizons of a section, which is also why it is important that before we conduct a survey, we require privy information about the field to understand VFS and the deposits, the type of deposits, the type of formation, and the history or geology of the field before we go into any form of work. So that answers that question. Any more questions? How sensitive the method to the accuracy of the subsurface velocity model? What is the lateral and the vertical resolution? Yes, okay, so this question has been asked a couple of times, and with regards to how sensitive is the method to the accuracy of the subsurface velocity model. So the subsurface velocity model that we are creating, first of all, is to create an actual spectra. And what that does for us is it gives us access to understand, what we're to expect from the field data. So we would have a field data that will actually be quite sensitive in recording, and that's why we always require that it records for at least a period of not less than 12 hours. Then we now compare this with the subsurface velocity model. And the subsurface velocity model, one of the reasons why we put the water, simulate with water or without hydrocarbons and with hydrocarbons, is because we want to test what sensitivity will be. So there's a lot of iterations of work that will be done in that section. With regards to the resolution as a guidance, we take the vertical resolution of the field, and we do a 1/4 of the total depth that you'll be looking at. So, for example, if you had a reservoir depth and you had a certain number of OBSs, what you'll be looking out for is what's the distance or what's the depth of resolution that you can get from each formation as opposed to the total depth of the target. So if we're looking at, say, a target depth of about 3,500, our vertical resolution for that formation will be between 300 meters, thereabouts. But this is something that I can address properly and get back to you. Is this Lev, if you can just take the name of the person who's asked that question, please.
Yeah, that would be Alex.
Okay. Then do you have an example where you are able to compare LFS with results from AVO? I'll probably be able to get them. I don't have one here with me. So amplitude versus offset tells you where you can possibly see through looking at the near, the mid, and the far offset and the identification of fluids across the AVO. So that's something that I don't have an example here right now, but it's an interesting question. I'll need to look for field data where comparisons have been made with AVO and LFS data. So Morris, I'll get to you back on that question. Okay, if that's it, I would like to say thank you again for everyone who's attended. For all the questions that have been asked, I will come back to you and we'll address them in this in more detail. Lev, if you can just please copy the names and the details of the people who've asked the questions, and we can get back to them. So thank you to everyone who attended the webinar. For time constraints, we weren't able to answer some of the questions, so I've created an extended version to answer most of the questions that have been asked. So a question from Alex says, how sensitive is the method to the accuracy of the subsurface velocity model? Now, although accuracy is an important factor, the model is reviewed and adjusted based on the low frequency seismic data that is recorded in the field. So especially on the calibration recordings that are done close to the current wells for which VSP data was provided by clients. So for various reasons, the original velocity model might not be always perfect for LFS to achieve reliable results. However, a 5% deviation of layers velocity during numerical simulation does not critically change the resulting spectrum. So at least you'd be within a very good range of accuracy. 2, what is the lateral and vertical resolution? Another question by Alex. So as a guidance, the lateral resolution of the reservoir equals the radius of the border effect and is 1/5 of the reservoir depth, TVDSS, time versus depth of sea. As such, the smallest size of the reservoir, which potentially can be detected, should be about 1/5 of the reservoir depth. So for reliable identification of the reservoir, the size should be at least, something between 2/5 of the reservoir depth. And for vertical resolution, as a guidance, the vertical resolution of LFS is about a 1/8 of the depth of the target horizon. So in other words, if LFS says that in the depth of 2,400 meters, we highlight hydrocarbon-bearing reservoir, this reservoir can be in the range of 300 meters. Another question by Morris. Do you have an example where you are able to compare LFS with results from AVO? Unfortunately, I have checked and we do not have such examples. Although we did have some blind tests where operators compared their results obtained by other methods with LFS results. They did not provide the exact source of other analysis, so we can only speculate. However, after comparison, they still went ahead with the LFS results. Next question by Cordelia. What are the sensitivities to thickness, reservoir, and or fluid column? So a lot depends on the type of hydrocarbon in the reservoir. But as guidance, LFS is able to identify reservoirs with thickness from 2 meters. So for gas, it might be lower. For heavy oil, it might be higher. So the bigger the thickness, the brighter the image will be. But LFS will not be able to confirm the exact thickness of the reservoir. Another question, is there a maximum depth of hydrocarbon accumulation that could be detected with LFS? So there's no exact depth maximum. However, LFS is most efficient for use on reservoirs from 800 to about 4,000 meters in depth. And the maximum depth where LFS was successfully applied was just over 5,000 meters. So the deeper the reservoir, the less accurate is delineation due to border effect for low frequency. Also, if there are multiple layers saturated with hydrocarbons, the quality of the analysis of the deeper layers will diminish with deeper depths. I think that ends the questions. So I'd just like to add at this point that LFS is a sensitive method, but it has its limitations as well. First of all, the reservoir should be of a detectable size and thickness, and the quality of oil is a factor as well. You know, where we have oils with API of under 15, these will be harder to detect because they basically have almost same density water. So the complex geology can be a factor as well if the velocity model does not reflect it properly. So proper data acquisition plays an important role as noises will need to be filtered out. And overall, we would need sufficient amount of raw data in good quality from the client to be able to deliver very good, meaningful results. Thank you again for joining. We look forward to you joining us on the part 3, where I'll be talking about full wave location technology and its use in fracture monitoring, fracture propagation, and fluid monitoring, fluid that's been injected, such as CO2 or any form of fluid into the reservoir. Thank you and have a good day. Cheers.